Good morning, everyone. This is Charles Ely. Today we're gonna be covering the requirements in COMNET Chapter 5. These deal with the default energy tariffs that we've developed. And today's presentation will be given by Snooler Price, who's one of the principals at E3 in San Francisco. And they did the work on this. They're also the group that's responsible for California's time-dependent valued energy metric. So with that, Snoo, take it over and we'll get started.
Great, thank you very much, Charles. Again, my name is Snooler Price with Energy and Environmental Economics, or E3 in San Francisco. I'm going to walk you through the sort of methodology and basis behind the Chapter 5 of the COMNET energy evaluation components. The goals of the COMNET TOU energy evaluation project was to develop for the whole country region-specific TOU energy costs for commercial buildings for COMNET. And what we were intending to do and did was to develop a methodology that looks at building performance on an energy cost basis. So while Energy Star performance rating and other sort of rating methods and building performance metrics have been historically linked to energy use, either source energy or site energy, COMNET really focuses on energy cost basis. So when you're looking at energy costs of electricity, natural gas, and other fuels delivered to the building, the cost to deliver them really varies by both location, where you're at, and time of energy use, when you're using energy. And so the whole methodology we're going to walk through in COMNET is really focused on picking up that and how did we evaluate that and develop sort of a workable energy cost basis for the COMNET standards. Because we're doing an energy cost basis while Energy Star performance rating is in source energy, we have a different metric, and so you can get a COMNET adjusted performance rating from Energy Star, and we'll talk a little bit about that as well. So the scope of the project, and you will see this when you look at the Chapter 5, is that we developed basically default values for energy by four different fuels: the electricity, natural gas, and then steam and chilled water. So for the electricity piece, what we try to do for each of the DOE climate zones is look at the actual cost of electricity. What does it cost to deliver a kilowatt hour by season in the peak of the day, mid-peak, and off-peak? So that probably looks quite familiar to a number of people who are used to looking at utility tariffs. There are time of use periods in many utility tariffs and with different costs. We're actually fundamentally trying to capture the same thing. It's higher cost to deliver energy on peak because of all the infrastructure required. So the cost differentials reflect both higher energy cost, worse heat rates in power plants, as well as additional infrastructure that needs to be built to meet the peak load. For natural gas, there's less day-to-night volatility, but there is seasonal volatility linked to demand. So the natural gas values are higher in the winter than in the summer, which is the heating season. There's less volatility, but still there are seasonal costs in the COMNET valuation. And then finally, we developed the cost for steam and chilled water. And those costs of developing steam and chilled water, are closely correlated to the natural gas price shape. So you will see in there also seasonal cost differences. So I think I mentioned already, but why use a TOU cost basis rather than just an average rate? What we're trying to do is reflect better the societal cost of providing energy to a building. And with efficiency and improvements to buildings looked at on this basis, we get a more efficient building from a social value, kind of a societal value perspective that can help building designers design buildings that are less impactful to the grid and provide overall economic value. In many parts of the country, the actual retail tariffs reflect the same underlying cost basis that we developed here, so there's a lot of similarities. But what we did is we took a standard method for developing the cost differentials for each of the regions in the country and applied them. So the framework is consistent. It's not one utility tariff versus another utility tariff. It's kind of generic, if you will, time of use pricing for all regions in the country. And when you do this and you take into this perspective, you get quite a different answer when you're evaluating some advanced building features such as daylighting, photovoltaics, thermal storage. Those energy measures or efficiency measures or building features that tend to reduce your on-peak consumption. So the scope of the project, probably many listeners have seen this chart. It is the DOE climate zones. And so we have developed the COMNET values for each of those. From north to south, they start at 1 and go sort of up 2, 3, 4, as you can see. And then there's also east to west, sort of a moist and a dry and a marine. So probably many folks have seen this table. When you open to Chapter 5, you will see a set of 2U value tables that are essentially the answer. What it gives you is life cycle voided cost by the dimensions we talked about. So for electricity, it gives us by season, summer, fall, winter, and spring. The weekdays and weekends are defined separately, and then there are peak, mid-peak, and off-peak values for each of the time periods. For electricity, gas, steam, and chilled water are simpler. There's just a low demand season, which is the summer, and there's a high demand season, which is the winter. I guess I should say, so to use these values, these avoided costs can be basically entered into the simulation tools, and imagine Charles et al. Have methods to do that, and then the simulated consumption of your building multiplied by these will give you a sort of a COMNET total value. The other thing that can be done is that the COMNET lifecycle benefits, calculated as I just described, can be converted to source energy for use in the EPA target finder. So there are a set of adjustment factors listed again in Chapter 5 for a lookup on how to do that. And there is a unique adjustment factor for each basically pairing of building type and climate zone. So what you would do is you would get your COMNET lifecycle benefit, then depending on your climate zone and building type, look up the adjustment factor, multiply across, and it will give you a source energy number. I should point out that if there are standardized load shapes behind each of these building types and climate zones, and so to the extent your building that you're modeling has a better load shape than the standard, then that will translate through when you multiply by this into a better, lower source energy consumption result. So how did we develop all of these? Essentially, we divided into each of the sort of the 4 fuels. Most of the effort, because of all of the volatilities on the electricity side, to do the electricity piece, we chose 16 cities that are closely based on the DOE commercial building benchmark study. Because of data, I think we had to use Washington, D.C. rather than Baltimore and Fresno rather than Las Vegas, but basically picked the cities. And that gives us a point on the grid to look at what the costs are. We calculated the time of use periods based on marginal cost in each of those hours in each of those cities. Then We also looked at the natural gas delivered to each of those regions, and then with the natural gas, we obviously can compute the natural gas piece plus the steam and chilled water savings piece is linked to the natural gas, kind of for a district heating or cooling. So to define the seasons, they're obviously need to be defined by the climate zones. Months are grouped into heating degree days and cooling degree days to define what summer, winter, spring, fall is. So the months involved vary depending on where you are at. Then we define the TOU period statistically, basically clustering those hours that have similar marginal cost. This is not that different than what our shop E3 would do for a utility that was trying to define TOU periods for their retail rates. For natural gas values, we use the sort of national index, which is Henry Hub in Louisiana. It's the most liquid and commonly traded point of natural gas in the country, from which gas deliveries around the country are indexed. Gives us a seasonal shape, so by month, that we can compute. And then we look at the basis differentials between Henry Hub and other locations in each of the zones. So essentially we build up the natural gas price just like you would if you were a commodity trader trying to forecast what the price of gas was delivered into each of the zones. On steam, again, we link to natural gas. Essentially what we look at is, or thinking about in terms of steam value, is a district heating where the generator is in a cogeneration mode and there's excess heat that's being distributed. And because of the cost of the generator would likely be running on natural gas is higher in the winter, it leads to higher cost steam. There are some efficiency assumptions baked into that basically get us, well, how much does it cost by season to deliver that steam? And for chilled water, we do a similar thing. Basically look at if we were to take that steam and instead chill water, what would the cost be there, and so on. One thing that has been a source of confusion, our high season for chilled water is still defined as the winter because that's the underlying fundamental cost. So high season for cooling is obviously the summer, but for the value, the definition of the seasons in COMNET, so we are looking at life cycle costs. So there are a number of assumptions, as you might imagine, building into that. We've got a discount rate. We used a real discount rate and a project lifetime of 15 years. For most uses of COMNET, the actual life is not that critical. If we did a longer term, but then levelized it, or if we're to do a comparison across buildings, it gives us 1 point, but it doesn't really change the comparison of 2 scores if you're going to do just as long as this is consistent throughout the analysis. So the main data for the electricity piece are the utility load and what we call system lambda or market data, and FERC publishes that, so it's a public data source for all of the regions. The weather data to define the zones is NOAA. Then we do make a number of assumptions around power plant and characteristics, which are from the Energy Information Agency, EIA, which is part of DOE. We do have an estimate of what the value of carbon is embedded in all of this, and we use Synapse, which is sort of a meta-analysis of forecasts of the value of carbon. We add also T&D, well, basically expected, avoided T&D infrastructure if we can keep peak loads reduced. And we've done a lot of work on that in California and use those values. And then, as I mentioned, NYMEX for the market gas data, and Energy Star for the conversions and the steam and chilled water. I'm not going to go through this table in detail, but essentially it just lays out well for each of those climate zones. Where did we go to look for the market energy prices, the hourly load profiles, and the weather data for reference. I mentioned the natural gas price forecasts. Essentially, we looked at the NYMEX data and then forecast out into the long period with the EIA, and then do some extrapolation just so that to get to the very sort of long-term forecast. The value of carbon and forecast embedded in this is shown in this chart. Basically, pretty straight line increasing over time. I should say that the value of carbon is included in all 4 fuel types: electricity, natural gas, steam, and chilled water. So that is my quick run-through. I have a number of appendix slides if folks want to have in the Q&A session a little broader discussion or dig into this deeper. So maybe I should turn it back to you, Charles.
Well, thanks, Miller, for that excellent presentation. We will we'll now open it up for questions.